Hey, my name is Dan. I'm a postdoc at SDU. I'm going to tell you about this work that we're doing on fully out of order choreographies that I'll be presenting at ECOOP this year. Let's just jump into it. To start, I should explain what are choreographies and what's choreographic programming. So let's say you're a distributed application developer. Maybe you're making a distributed AI training system. And what you'll have maybe is a couple of worker servers, worker machines that are doing jobs, and you have a centralized server that's issuing the jobs to those workers. So you might have a situation like this. This worker has just finished a job. It sends the results to the server. The server sends it a new job. Likewise with worker two. But in practice, of course, you usually don't have the luxury of these diagrams. What you actually have is code. And so to understand what's happening in the system, you trace through the modules in your system. You might start at worker.java and say, oh, it sends something to the server. Let me open up the server.java file, jump over here. Okay, I receive a message. Then I send something back to the worker. I switch tabs back to the worker code. And likewise over here, I go from the worker to the server, from the server to the worker. It's annoying tabbing back and forth. Everybody's had this experience. And what we'd like, ideally, is to have some kind of single module, some kind of programming language we can write that will generate that code on the right. And that thing on the left is called a choreography, and you can write it in a language like Choral. This process of compilation is called projection. And the thing on the right is what we call endpoint code. And in the case of Choral, we're generating Java code. Nice thing about choreographic programming is that it's guaranteed to be deadlock free. All your programs are guaranteed deadlock free. You won't have message typing errors, so never a situation where I send you a string and you expected an integer and it causes you to crash. And you also arguably get cleaner code. You compare the code on the left to the right and make your own decision. But is this fast, right? How fast is the code? Well, let's look at the server code that we generated for that particular choreography. And I want you to pause the video here and stare at this and see if you can figure out or come to your own conclusion about what the issue might be with this code. To me, the issue is that we have a blocking receive on line 183. That means that the server has to wait for worker 1 to get it a message, to give it a message on 183, and only once that message arrives can we actually do anything with that message. So that means that on the right, if worker 1 is slow for some reason, then it doesn't matter how fast worker 2 is. Worker 2 is not going to get any results back until worker 1's message arrives. And you might say, oh, could we flip the order of the code so that this doesn't happen? But then of course, now you have the opposite problem. Worker 1 depends on how fast worker 2 is. What we want actually is implementation of the server that will dynamically change the order of these statements depending on the arrival order of the messages. And that sounds really complicated, but we can actually achieve it very easily without changing the code much if we use futures. Oh, I should say, so this kind of process that can change the order is what we call a out of order process. And a choreographic language that compiles to out-of-order processes is what we call fully out-of-order choreography. But like I was saying, we can make the server out of order by just using futures. So what I've changed the code here to say is on line 183, now worker 1 the server receives a message from worker 1 and binds it to a future. And then it sets a callback for the future. For whenever the message arrives, we're going to run this callback. And this gives us the nice out-of-order behavior we want. As whenever worker 1's message arrives, we fire this callback. Whenever worker 2's message arrives, we fire the callback. So perfect, right? We've solved the issue. All I have to do is patch the compiler, deploy it to production immediately, and then I go off and enjoy my Friday, right? I wake up at 3 a.m. with 6 missed calls from my boss. I check my texts, and I see this. Client is reporting corrupted data. Somehow my tool tweeted the CEO's password. What happened? So the point of this talk is to say that if you combine futures with choreographies, naively, you're going to get these really insidious race conditions that we call integrity violations. But all you have to do to prevent those race conditions is add something called integrity keys. And once you do that, you get all the performance you want and none of those particular terrible race conditions. Not all the performance you want, but you get the picture. You get some good performance. So what went wrong, right, when our tool tweeted the CEO's password? So in this example, this didn't really happen to me, of course. We've got a few microservices. We've got a microservice called the content service, and it's responsible for just generating tweets, content for tweets. And we've got a key service that manages all the social media login information. We've got a router service, and its only responsibility is to forward data around. And we've got a worker service who's actually responsible for calling out to the Twitter API, the X API, whatever. And so when we implement this choreography in this tool, we have on line 2, the first thing that we do is the content service sends the tweet over to the router. So I should explain this notation on the left. cs.tweet, that's the content service, and tweet is a variable that's located at the content service. And this arrow means that we're sending a message to the router, and we're binding the content of that message to the variable tweet at the router. And that generates the message on the right, where the content service is sending data to the router. Then on line 3, we have the key service sending the credentials, so the login information for the Twitter API, over to the router. And then on lines 4 and 5, we have the router sending the tweet to the worker and the credentials to the worker, and that gets you the code on the right. Or it gets you that code on the right if you are using an ordinary traditional choreographic language. But remember, we've patched the compiler to generate futures. So instead of waiting to send the tweet until we get the credentials, we're going to, oh yeah, and also the worker posts the tweet once it gets those results. But so because we patched the compiler, we're actually going to get this behavior over here, where as soon as we receive the tweet at the router, we're going to be able to forward that to the worker. Likewise with the credentials. So if we look, where's the bug still, right? We still haven't seen it. So if you look at the compiled endpoint code that we get for the router, we see this. First, we receive a message from the content service. We bind it to a future, and that's going to be the tweet. We receive a message from the key service, and we bind that to credentials. And we set these callbacks on line 4 and 5. It seems fair enough. And this gives us the out-of-order behavior that we wanted, right? If the credentials arrive first, then that callback on line 5 will fire first. And if we receive the tweet first, the callback on line 4 will fire first. But did you see the order of the messages will change? It depends on the arrival order of those two messages. I wonder if you see what the bug is yet. Let's look at the worker now. We see that the worker receives a message from the router, and that's going to be the tweet. And it also receives another message from the router, and that's going to be the credentials. And then it's going to post once it has those two values. You see the bug yet? If you look carefully at the worker, you'll see on line 2, it's receiving the first message, and it's binding that to the variable tweet. But the first message is not necessarily going to be the tweet, right? It could be the credentials, depending on the arrival order. And that would mean that if the credentials arrives first, it gets bound to the variable tweet. And the tweet will get bound to the credentials. And we have this situation where we end up posting, tweeting the CEO's password. And so this example where data is being bound to the wrong variable, that's what we call a CIV, a communication integrity violation. Really nefarious bug, I would say. But it's pretty easy to fix if you think about it for a second. You just need to attach a bit of extra data to these messages so that the recipient will know what the meaning of that message is. Because we couldn't rely on type information, by the way, right? These are both strings. So now we're making sure that the router, whenever it sends credentials, it will always attach the number 2 to it. And whenever it sends a tweet, it'll always send the number 1 with that message. And so the worker code that we generate will just say, whenever I get a message with the tag 1, that's going to be the tweet. When I get a message with tag 2, it's going to be the credentials. It doesn't matter what order those messages arrive. Awesome. Now we won't get this communication integrity violation. So we have to patch the compiler to generate these numbers to make sure that you don't get these kinds of issues. So the first big takeaway from our paper is that you can prevent these CIVs inside of a choreography by attaching these statically unique IDs that identify the meaning of the message. But there's actually more. Here's a different example where we have an online checkout type of choreography. Some new services now. We have this billing microservice, and this guy is going to charge your credit card in the transaction. But before he charges your credit card, he sends the user ID, your user ID, over to the shopping cart service. And this shopping cart service is sending the total price of all the items over to this currency exchange service. This is kind of a common interaction. And the currency exchange service is going to convert everything to US dollars using the latest data, and it's going to send the total in US dollars back to the billing service so you can charge the card. And now, in a real implementation of this, you might actually have multiple services, multiple replicas that have shopping carts on them. And so when we run this choreography here, we have me, this is my particular transaction, and the billing service is sending my user ID to shopping cart replica number 2, because that's where my shopping cart information is located. Okay, we get the user ID, and then I have racked up a $1,000 charge for all the things that I want to buy. Send that to the currency exchange service. The currency exchange service doesn't do anything because it's already in US dollars. And now the billing service can charge me the $1,000 that I owe. And then when Marco comes along and makes his own transaction, he'll do the same thing. The billing service will send the Marco ID, and then it sends the €5 that he wants to buy. Now, the issue with a traditional choreographic language is that Marco's transaction cannot be interleaved with my transaction. The billing service has to wait until it receives the currency exchange data before it can handle Marco's data, because we have blocking receive traditionally in choreographic languages. But once you patch the compiler to use futures, now we can get this nice interleaved execution. And this is something called pipeline parallelism, and it's really good. It's a huge win for performance. But there's a really insidious issue here as well. Look at what happens depending on the order that messages arrive at the currency exchange service. So I wonder if you caught it. It's very subtle. So the $1,000 now arrives second at the currency exchange service. And that means that the order that the messages arrive at the billing service has changed also. And before, the first message was the $1,000 for my transaction, and now the first message to arrive at the billing service is Marco's $6. Let me show this again. So I'm changing the order in the currency exchange, and look at what happens at the billing. Before, the $1,000 arrives first, and now the $6 arrives first. So this is another version of the sieve that we saw before, right? Where we now have two integers that are coming in, and the billing service has no way to know which integer corresponds to which transaction. And so as a result, if you write the compiler improperly, you might make the mistake of assuming that that $6 pertains to me. You charge me $6 for my $1,000 purchase, and Marco gets charged the $1,000. That's really bad, right? And so to fix this, though, if you think a little bit more again, you can think, oh, well, maybe we'll just attach now for each of these choreographies, we'll have something called a session token. And this will uniquely identify which message corresponds to which choreography. And so because all of Marco's message have the tag T2 with them, when the billing service receives T2, $6, it knows that that $6 was actually for Marco, not for me. And so this is how we can fix this kind of sieve between procedures. So this is the second big takeaway from our paper, is that you can prevent sieves between choreographies with dynamically unique session tokens. These are generated dynamically. So that's all the time I have. I'm actually over the time limit, so I'm going to have to practice this talk a little bit more. But the takeaways, I should point out, I should talk about what's in the paper now. So in the paper that I don't have time to talk about at all, one thing that we have is a formal model that explains all of this. And in particular, one of the things we do in that formal model that I didn't even get a chance to tell you about is how you generate those session tokens. And if you think for a bit, you might think that you need to do some kind of synchronization to generate these session tokens, because all of the participants of the choreography, they need to agree on the session token before they enter the choreography. And so you would think that somebody generates the token and sends it to everybody else. But actually, you can do it without this synchronization by trading off a little bit of space. And so we show how you can generate these session tokens and prevent all kinds of sieves without introducing any extra synchronization. And of course, we prove these results. We prove the standard results of deadlock freedom. We show that choreographies and the processes they generate are by simulation. And we formalize the property of communication integrity, which we're trying to preserve. And also, we've implemented this in code that you can now use. I've added a library to Coral that will allow you to use futures in Coral and combine them with these session tokens and these IDs to prevent sieves. And so we've got some data, we implement some micro benchmarks, we have a larger, pretty interesting AI model serving example, and we get some pretty big performance wins there. Probably, obvious, but we have it, so there they are. So wrapping up, I want you to remember the big takeaways again. Number one, that inside of a choreography, you can prevent sieves by attaching these statically unique identifiers, like we talked about in the first example. And between concurrent instances of the same choreography, you can prevent sieves by attaching these session tokens. And so if you want to prevent all sieves altogether, all you have to do is attach these statically unique IDs and the session tokens. Those things together are what we call the integrity key. And the integrity keys prevent sieves. So that's all. Again, you can read the paper over here. And also, if you're interested in this kind of thing, you should join us on the Zulip channel here. This is the multi-party languages Zulip, where we talk about choreographic programming and other kind of distributed programming languages. Yeah, that's it. Thanks for your attention.